Okay, what we're going to be looking at today is we're going to look at Lenz's law. So I'm just going to put up the PowerPoint for Lenz's law. So these are the 2 dot points in the syllabus. We need to account for Lenz's law in terms of conservation of energy and relate it to the production of back EMF in motors. So there's essentially 3 parts to this. We need to look at what Lenz's law is. We need to understand how that relates to conservation of energy. And then we need to link it back to back EMF, which is in motors, because our motors are our application of the motor effect. After that, the second dot point is explain that in electric motors, back EMF opposes the supply EMF. So just understanding the application of it, how that back EMF actually affects an electric DC motor. Okay, so what we already know from last week, we looked at Faraday and his electromagnetic induction. So we already know that if we've got a coil of wire, conducting wire, and we have a magnetic field, if we move those relative to each other, we will induce a current in the wire. So that picture on the screen there, we've got the primary coil, which is, we have an input current into that. That's going to produce a magnetic field around it. That magnetic field is going to pass by the secondary coil, and because it's a changing magnetic field when it first gets set up, it will momentarily induce a current in that secondary coil. We'll get a reading, the reading will go back to 0. So that's Faraday's initial experiment. And if we can keep that magnetic field changing, then we can keep that induction of the current, we can keep that going continuously. Okay, so that was Faraday and electromagnetic induction. So Faraday and Lenz linked together really strongly. Okay, so Lenz's law, Lenz is a German scientist. So his law was whenever an EMF, an electromotive force, is being induced in a conductor as a result of changing magnetic flux, the direction of the induced EMF will be such that the current it produces gives rise to a magnetic field that always opposes the change and hence opposes the cause of induction. So that's really wordy and a bit long-winded. So what that means is if we induce a current, that current will be produced in a direction to try and oppose the initial change. So whatever change you make, that induced current will try and oppose that change. Okay, so we'll have a look at a few examples. So the example at the top, I've got induced current. So if we've got a magnet, in the top example, we've got a magnet and we're going to push it into a coil of wire. Okay, so there's no current flowing through this wire. As we push that magnet in, it will induce a current in those wires. Okay, and we know what direction it will occur because of Lenz's law. So Lenz's law tells us that if we're pushing a north in to our coil of wire, to oppose the motion, Lenz's law tells us that the current is going to set up so that it creates a north at this end. That north will be opposing that north that's coming in. Okay, so that tells us from Lenz's law which way the current is going to go. The second example at the bottom, so if we take that same magnet and we move it away, the current is going to try and oppose the motion, so it's going to try and produce a south to try and pull that back. Okay, so we're opposing the initial motion, so the initial motion is move it to the left. The created magnetic field is going to try and oppose that motion by creating a south to try and essentially pull it back. Okay, so the second part was how it links into law of conservation of energy. So in a DC motor, as the coil starts to turn, we're going to induce a current. Okay, and we know that, so we know that we're going to induce a current in that coil as it starts to turn through the magnetic field. Okay, we know that for the law of conservation of energy tells us energy cannot be created and destroyed. So if the opposite of Lenz's law was true, so the magnetic field created by the wire, if that was if it was encouraging it to move in the same direction, we would induce more current in the wire, we'd create a stronger magnetic field, and so on. So the large current would produce heat, So at this stage, we've got no energy being put in, but yet energy is being created. It would sort of continuously go without any input of energy. We know that that can't happen, so Lenz's law must be true. So if we want to keep the law of conservation true in a DC motor, we need that induced current to oppose the motion. Okay, so that's how it links in with Lenz's law. So back EMF is basically that induced current in a DC motor. Okay, so in a DC motor, if we just look at this top part of the diagram, if we've got a DC motor and we're applying that's an example of an AC motor, so let's just pretend it's a DC motor. DC motor, if we're applying a current and we have a magnetic field, that coil is going to move. There's going to be a force on that wire, it's going to move. So now we've got a moving coil through a magnetic field. We're going to induce, so not only are we putting current into this coil, but we're going to induce a current in that coil, and that induced current will act to oppose the motion. Okay, so essentially it's opposing the rotation of the motor, the rotation of the coil. Okay, so that's called back EMF. So it's the EMF that's induced as it turns that's going to oppose the motion, which is a bit of a problem when we've got DC motors. All right, so let's look at a couple of examples. Okay, so in this first example, so part A, we've got a bar magnet, we're moving it into a solenoid. Okay, we should be able to determine which way that current is going to flow. Okay, so if we're pushing a north in, this solenoid is going to try to oppose the motion by creating a north on the outside. Okay, so if you use your right hand grip rule that we learnt in the prelim course, there's the answer for A. The current will flow in a direction that results in a north pole on the left side. Okay, so right hand rule, we're going to have the current flowing over and down. Okay, so it'll come up this side, around, and down. Okay, and that will, if you use your right hand grip rule, your thumb will be pointing out this way, so we're creating a north on this end, which will oppose the motion. Okay, so B, not the exact opposite. B, we've got a bar magnet and we're pulling it away. Okay, so if it wants to oppose that motion, it wants to pull it back. So same thing again, it's going to create a north on this side of the solenoid, and so the current is going to go same direction again. Okay, it's going to come up this side, down around, and down there to create a north at this end. Okay, because we're trying to pull that south back, trying to oppose the motion. Okay, so that's your answers down there, which is just what we talked about. All right, example 2, let's skip through this. A loop of wire in a magnetic field. If you've just got the magnetic field and a loop of wire sitting there, we don't have movement relative to each other, so nothing is going to happen. That's for part A. And part B, if the magnetic field increases, you'll have a changing magnetic field, and so you'll induce a current in that loop. Okay, and that loop, if you use your right hand rule again, then we can work out the direction that current is going to flow. Okay, so the thumb pointing out of the page, the fingers curl around anti-clockwise. Okay, so the current will flow in an anti-clockwise direction in that example. Okay, example 3, the direction of the induced current for those examples. Okay, so we have a moving wire through a magnetic field, so we're going to induce a current. So you basically want to induce a current that's going to apply a force in the opposite direction. Okay, so part A, if we're moving up this way, we want to move down this way. Okay, if you use your right hand rule, okay, I might just switch over, see if I can show you what I mean by the right hand rule. Okay, so if we've got a magnetic field, okay, and we've got a wire, and we want to move that wire up the page. Okay, so V, we're moving it with a velocity up the page. Okay, so let's see if we can figure out our right hand rule. Okay, so we've got our magnetic field going into the page. Okay, and we want to create a force down the page. Okay, so if we create a force down the page, means that the current must be going across. Okay, so we want to oppose the motion, so we want a force going down the page. Okay, so the current will flow across this way. That will be our current to oppose the motion going up the page. Okay, so example 2, we've now got magnetic field coming out of the page and we've got a wire. Okay, if we're going to, let's do the same direction again. If we want to move it up the page with a velocity, now we've got our magnetic field, a bit close, magnetic field coming up out of the page. We want to create a force, magnetic field, we want to create a force going down. Okay, so now our current is going to go across the page, okay, the direction of my thumb. Okay, so that's going to be the direction of our induced current, which is Lenz's law. Okay, see how you go with that? Let me know.